right. Well, we're fortunate today to have Nicholas Shorter to give a presentation. I didn't realize at the time I was asked to do the introduction, but Nicholas and I had met back in 2004 when he had a class with me at UCF. So it's kind of nice to see Nick again. Nick did his bachelor's and master's at UCF. Bachelor's in 2005, master's in 2006. He also did the PhD, which was completed in the summer of 2009. And all this work was in a theme that feeds into this talk. For his master's thesis, he proposed a novel method for unsupervised reconstruction of irregular LiDAR data. And for the PhD work, he proposed unsupervised methods for building detection from LiDAR data, building detection from color, nadir aerial imagery, and registration of LiDAR data to aerial imagery. Harris picked up on this, offered opportunities for seminars, and ultimately even funded the dissertation work. So it was a real foot in the door, I believe. And since graduation, Nick has been working as a software engineer in Harris Corporation. I'll hand this over to Nick and let him introduce the actual talk.
Thank you. Today's talk is entitled Pseudo Homotopy Trees for Unsupervised Building Detection in Irregular LiDAR Data. I have the research website hosted up here, nshorter.com. A lot of my publications have been hosted up there. One recently got accepted into the MDPI's remote sensing about building detection from aerial imagery as well as unsupervised vegetation detection. So feel free to check out there for any publications, or I think I have one piece of code that's up there from my dissertation. So for the presentation, first I'll give a brief overview of what exactly light detection and ranging data is. It's, I think in the US, you'll typically see it referred to as LiDAR, and then sometimes in Europe, it's laser ranging, or they call it LiDAR. LiDAR, it's the same thing. We'll go over some motivation. Why do we want to do building detection in an unsupervised fashion? What meaning does it have to the industry and the rest of the world? And then what is exactly homotopy trees? And then I wound up slightly making a variant of that and then using that variant and dubbing it pseudo homotopy trees. There's some properties we don't retain from the actual formal homotopy tree concept that's in set theory and math. Then we'll be going over how do we use these homotopy trees to identify buildings and non-ground and ground. And then some experiments. We'll discuss the results and some conclusions. So what is light detection and ranging data? What happens is the plane will fly over a given terrain, and this plane will contain a global positioning system, an inertial navigation system, and a light detection and ranging, or LiDAR sensor. The LiDAR sensor will emit a laser beam. The laser beam will interact with the terrain, and then it will return to the LiDAR sensor. It's emitted out of the emitter and then returns into the receiver. The LiDAR sensor will record the time difference that it took for the laser beam to be sent out and then returned. From the global positioning system, you'll get the longitude and latitude. From the inertial navigation system, you'll get the height of the plane. And then finally, from the LiDAR sensor, you'll get the distance from the plane to the target. From the collection of these three sensors, what you can do is, in kind of a sense, you can think of a LiDAR sensor as an analog to digital converter. The terrain is our analog scene. We want to create a collection of irregularly distributed three-dimensional points. The points are irregular. They're not in the form of a range image. When you get the LiDAR data, it typically comes as an ASCII point file, and it's a collection of points that are regularly distributed. Sometimes you can interpolate them, but people will argue that interpolating the fixed points to make use of conventional image processing algorithms, you're introducing interpolation error. So you'll see both sides of this event. Some people say, well, keep it irregular, and then you won't lose any of the data. Other people will interpolate it to exploit the power of conventional image processing techniques. But the LiDAR sensor creates a collection of irregularly distributed three-dimensional points describing the given scene. I talked about the fact that how we get the longitude, the latitude from the GPS, and then the range to the target from the INS and the LiDAR sensor, INS inertial navigation system. You also have this concept, what's called first and last return pulses. What will happen is when the laser beam is emitted, some of the laser beam will interact with the top of vegetation, while other portions of the laser beam will penetrate the vegetation, and then you'll get two return beams. If your sensor is good, some of the sensors will actually record multiple returns, and you'll get first and last return pulses, where first correspond to the top of the buildings and last return corresponds to pulses that manage to penetrate the vegetation. You'll see lots of first and last return pulses or high first and last return pulse differences for vegetation, whereas you won't with the tops of buildings, because you're not going to get any penetration. But the beam will hit the top of the building, and then the whole beam will come back mostly all at once. You also get the return laser intensity sometimes. Again, this is based on the sensor. You're almost certain to get longitude, latitude, and elevation, but then based on the sensor, you may get first and last return pulses, and you may also get intensity. And researchers will argue that all of these are important features you want to include for your task. The more information, the better. The LiDAR system isn't perfect. There is noise, and it's coming from several different areas. The first is that you have limitations within the sensors themselves. The GPS and INS are only certain to so many meters or centimeters, and then the LiDAR system will actually have an accuracy how well it can measure the data that it's sensing. In addition to that, when the plane is flying and it's procuring the data, what we call it is like strips or swaths. The plane will fly over and it'll be collecting the given data, and it'll keep flying and it'll keep flying, and the longer it flies, the longer the strip. Also, the longer it flies for a given strip, the more the GPS sensor will experience a drift term, and the value will begin to drift from the true value. So that's another noise parameter you'll see. And then finally, there's two more. One is which, if the system isn't calibrated, you could have a misalignment between the INS and the LiDAR sensor, and this will be a constant difference. It'll be a constant offset in the height. The height will be off by a constant factor. And then also you'll have, and you'll rarely see researchers talk about this. It's rare to find this in the literature. Sometimes some people will allude to it, but most of the time they ignore it and live with the noise. But the atmosphere isn't a vacuum, as you well know. And when the laser beam propagates through the atmosphere distorts the true path of the laser. It distorts it by a little bit, but nonetheless it distorts it altogether. And you'll get the atmospheric distortion plays as another part of the noise. That is the reason why when you get a set of data, you'll notice sometimes there are no returns for the water, because when the laser beam goes through the atmosphere and then it hits the water, Snell's law is going to cause the mediums having two different indexes of refraction. The laser beam is going to completely diverge and then have a hard time returning to the sensor. So that's the reason why you'll get you won't see areas of return with the water, or sometimes noisy returns where there's glass in the tops of buildings. But and then another noise aspect is you'll get artifacts from non-uniform sampling from multiple strips. Because the GPS and the drifts, they'll go over and they'll procure a swath or a strip, and they'll turn around and they'll go and procure another swath and keep turning until you get like the coverage that you need. And these strips will sometimes not perfectly align with one another, and then you'll get a misalignment, and then the strips will have it'll appear non-uniform. The building edge won't appear exactly horizontal. You can register the strips, and I believe George Wasserman and some other people in the literature have actually actively talked about registering the strips to correct this error. So what is the motivation for building detection in LiDAR data? Why is this important to us? It's important for several different applications. Imagine there's a natural disaster like Katrina. Let's say you sample the scene before the natural disaster occurs, and then you sample the scene again. Then you can automatically identify which buildings were affected by the natural disaster through some means of change detection. You can also do like an urban planning analysis. You can detect where the buildings are and then plan where you want to build future buildings. If you know where the buildings are, you can have optimal cell phone tower placement. There's also applications for virtual tourism and geographical information systems. The important thing here, and this is something that the industry is striving for, is to actually minimize the amount of user intervention in this building detection process. You'll sometimes see algorithms that'll have tunable parameters, but the idea is at the end of the day, you want an algorithm that'll serve as a black box. You feed in the data, it automatically detects the buildings, you get the output. The more tuning, the more manual intervention, the more you're adding cost to have an analyst sit there and perform those tasks for you. The idea is to eliminate the analyst or cut your overhead. And this is what the industry is looking for. You'll see this motivation reflected again and again in the literature. So I mentioned in the beginning of the talk homotopy trees, and before we get into that, let me just a moment describe what we're going to define as connectivity. When I say something is connected, or two sets are connected, what I'm talking about is, let's say you have a set of triangles. You have the light gray set and then the dark gray set. We say any two triangles here are connected, or they belong to the same set, if you can connect those triangles, and the path you get through those triangles all contains triangles within the same set. So like here, any of the two gray triangles, you can draw a path and connect them, and as you traverse that path, there's only gray triangles in that path. But you can't connect gray triangles to the dark gray triangles without going through the white triangles. Therefore, the gray and the dark gray are two different connected sets. So what are homotopy trees? Homotopy trees is a concept that's existent in topography or a set theory, and what it describes is the arrangement of space. So imagine Z contains all of the gray surfaces here, and the gray surface is like Z11 is this shape with 3 holes in it, and Z12 is this polygon with a rectangular hole, and then Z31 is that circle. So Z contains all of the space, and then Z complement contains all of the empty space. So then what you can do is you can construct a tree based on the spatial arrangement of the space. So here we have Z0. Z0 represents the entire unbounded empty space that's all all throughout here. Then you have two surfaces, Z1 and Z2. Z1 and Z2 are immediately adjacent to this empty space, and the adjacencies are represented by the arrows. Then the first component here actually corresponds to the generation, and the second component corresponds to the node index. So these are in generation 1. These guys are in generation 2. This one is in generation 3 of the tree, and this is in the first node, the second node, first, second, third, and fourth. And you'll see Z21, Z2, and 2,3 are immediately adjacent to Z1, so you have the adjacency arrows there as well. So the homotopy tree is a means through topography and set theory to describe the spatial arrangement of space. We're also going to be, in this talk, we'll be triangulating the LiDAR data. We'll take the irregular LiDAR data, we'll connect all of the points, which will make vertices, and that'll make a triangulated irregular network. And there are two types of triangles that I want to talk about that we're going to actually define in this talk for these triangles existing in this tin, triangulated irregular network. The first, and when I say triangulation, I don't mean like the satellites triangulating something. I mean like constructing the triangulated irregular network, a collection of tins describing the surface. And we're going to define a triangle which is called a wall triangle. And this wall triangle will be a function of the triangle's orientation and the difference between that triangle's lowest point in elevation and the highest point of elevation, or this H difference term. If the triangle's lowest point and highest point, the vertices, the lowest and highest in elevation, is greater than 1 meter, and its orientation is greater than 45 degrees, we're going to call that triangle a wall triangle. The orientation is the difference between the nadir vector, or the vector pointing straight up in terms of elevation, and the normal vector, which is normal to that triangle's surface. The larger the theta, the steeper the triangle. The smaller the theta, the low-level lying triangle. So we want steep triangles with a minimum difference, and that's called a wall triangle. If the triangle violates either of those conditions, that's called a non-wall triangle. Hence, the classifications are mutually exclusive. So then we're going to run down some definitions to go a little bit further that we're going to wind up using. First, as you gathered before, Z will be a connected set of triangles. And then if we have a connected set of wall triangles, we're going to call that a wall-connected set. A non-wall connected set of triangles, a connected set of non-wall triangles is called a non-wall connected set. If you have a non-wall connected set, or a collection of non-wall triangles, low-level triangles, low-lying triangles, that correspond to the ground, we're going to call that a ground-connected set. If you have a wall-connected set that's immediately adjacent to the ground, we're going to call that a first-generation connected set. And finally, if we use this function, this S of Z, this will return the size of a connected set in terms of its nadir area. When we look straight down and you look at all the areas of the triangles within there, that S of Z